Hey everybody, and welcome back to I Hate Chemical Engineering. This episode is the second episode in our Thermodynamics 1 series. I'm going to do a two-part series on Thermo 1 and Thermo 2 out of Smith, Van Ness, and Abbott. Their book is kind of the cornerstone book for many universities, and it's called Introduction to Chemical Engineering Thermodynamics. Again, I'm going to be using the 8th edition or the 7th edition in doing practice problems at the end of each, in the back of each chapter as we move forward. But given that this is the second episode, we don't really have many practice problems to be doing right now. So we're just going to roll right into it. Today's going to be on the first law of thermodynamics, which implies that we're going to be talking about the energy balance, as well as internal energy and enthalpy. So we touched on internal energy briefly in the last video. We're going to touch on it a lot more in this one. So let's go ahead and define the first law of thermodynamics. Well, the first law, and I don't want to do any drum rolls or anything like that. People like to put a lot of weight and emphasis on these laws. Like if you just know the law, you know thermo. It's not true. It's a lot harder than that. But the first law is simply put is that energy, all energy is conserved. It can be neither created nor destroyed. And what that means is that similar to the law of conservation of mass, this is now what we call the law of conservation of energy. You touched on that a little bit in Physics 1, talking about the transferableness of energy between kinetic and potential energy. Similarly, we extend that to be all forms of energy, right? So let's go ahead and remember our mass balance here, and just to make the metaphor a little bit more sound. So we have some mass entering into some system through a stream. Well, let's draw it like this. You have mass entering into a stream here, and into a control volume here, and out of a control volume here. And we've said in the past that the change in the mass of the system with respect to the change in time is going to be equal to the mass of flow rate of the stream entering the system. So we'll call this stream 1, and that's stream 2, minus the mass flow rate out of the system being that of stream 2, right? So the law of conservation of matter is really simple, really easy. You can do it. And just knowing a bare minimum of a few other things, you can know quite a bit. And in chemical engineering, a lot of times we're looking at steady state information, so that differential term will obviously go to 0 in that case. So making mass 1 have to equal mass 2, right? So the energy balance, which is similar, is a little bit more complex, being that energy can cross boundaries not just through physical forms of like matter, like input streams and output streams, but also through other forms such as heat and work, which we'll dive in a little bit on in the first part of this video. So before we move on too much further, let's go ahead and make another definition here. We're going to say internal energy. So internal energy. We're going to say that's all of the energy contained within the molecules of the substance. So unlike all the other state variables that we mentioned before, that the new ones, enthalpy, entropy, so on and so forth, This one has probably the least esoteric definition, in that it is simply just the energy of the molecules of the system, right? So if you, we'll talk a little bit more on what that energy looks like when we get to the kinetic theory of gases. I've got a pretty good video on that, but in general, what you would understand is that that this is just the energy of the molecules themselves. So if you take energy away, the molecules slow down. If you add energy, they speed up. Or something else. We'll talk more about that again, like I said, when we get to the kinetic theory of gases. But to say that is, when we're looking at a control volume, that's what you're interested in, is the internal energy of that control volume. So if we go back up here and said, let's take this same example. Let's just copy this, move it down again, and we'll just redo it for an energy balance. So if we take the same example here, we want to know, the change in energy with respect to time, and that's going to equal what? And we denote it this way as an MU, because obviously the mass of the system is going to matter. Again, we look at all of our state variables in terms of specific or molar variables for the most part. So we'll go ahead and say this is going to be equal to joules per kg, or joules per gram mole, or or their English equivalents. We'll put a capital T or lowercase t superscript to denote just plain old power, or energy. And then rate is going to have a dot above it, which is going to be the joules per second, right? Or that's, a watt, right? And that's just simply the power rate of the system. So, right here below, we're looking at the change in the internal energy over change in time of the control volume being the tank that contains that orange fluid here. Right. So how could energy move in and out of that system? Well, there's quite a few different ways to do it. We have the physical ways through the flow streams of 1 and 2, but also we have some less physical ways in terms of through matter transfer, that is. So let's look at the non-transfer of matter ways before we go into dive deep into the matter transferable methods. So first off, you might have a coil, let's say in a system, a tank or something like that. You might have a coil that has liquid, cold or hot liquid, let's say, flowing in and out of this coil. And that coil might be transferring heat out of or into the system. If you think about it, this is a really straightforward example, because if you touch, it goes back to what you've learned about maybe heat exchangers, right? Or the like. So you grab a glass of cold water, your hand's going to get cold because energy or heat will be leaving your hand and going into the water. Similarly, if you touch a hot stove eye, energy will be leaving in the form of heat the stove eye and going into your hand. In chemical processes, we often have heat exchangers, or coils, internal coils, that do such a thing, right? And they transfer heat, and we call that heat, or denote that heat, as Q, right? So Q is the rate at which energy enters into the control volume. So we want to specify that it's into the control volume. So and that's Q dot for the rate again, and that's in joules per second, or you could say Q in joules per kilogram, or joules per mole. Similarly, through the control volume, you can have a agitator or a turbine, which what it will do through a motor is spin and stir the fluid, and that will impart energy into the fluid, not via heat transfer means, and not via matter means, but by physical mechanical means will energy be imparted into the fluid. And we call that shaft work. So we denote that as W subscript S, again in joules per second, or W subscript S in joules per kilogram, or joules per mole. Now, to figure out exactly how much energy that goes into the fluid in those examples is based on, kind of vendor documentation from like the agitator piece of equipment, or, there's a couple other, ways to look at it. Like if you're looking at a pump, it's actually spinning a blade and increasing the pressure of the fluid, and that's adding energy to the fluid. So, how much energy is it adding? Well, you got to think, okay, my motor is going to be outputting 5 horsepower, and 5% of that or whatever is going to be going into the environment as heat, and another, literally the air around the motor, and then there's losses between the blade, efficiency losses, you could say, between increasing power. And the remaining, doing useful work, so that'd be increasing pressure. And then, so you could say some amount of it's going to increase pressure, some amount of it's going to increase heat, or get caught up in friction in the bearings of the agitator, let's say. So it's not always straightforward, but that's what we call shaft work. So far, we can include both of these terms. So we have, again, our equation. We're going to extend it. We're going to say the differential change in energy versus change in time of the system is going to be equal to the amount of energy added via heat plus the amount of energy added by shaft work plus something else, right? And that's question mark we haven't yet got to. So I'm going to pause right here and say the next grouping of materials is going to have to do with the flow streams, and I'm going to break it up into two videos. So the next half of this video is going to be on the stuff that's pretty straightforward, and the last half is going to be what we call flow work. Flow work will have its own video, and then we'll end with the definition of enthalpy. So let's redraw our system again. So we have our system here, and we want to know how fluid is that is flowing into our system is imparting energy into our system, right? So again, we're looking for what's the rest of this question mark in this equation. Well, there's one thing that's maybe straightforward to most of you all. Well, is the internal energy of the fluid that's entering and leaving. There is already internal energy in there. So again, part of that question mark is going to be the mass flow rate of stream 1, again, times the internal energy of stream 1. And that's going to go directly into the internal energy of the system, as well as what will be leaving will be taking out of the system. All right, so that's should be straightforward. So we'll just go ahead and denote this here. Another piece of energy in the system is going to be the kinetic energy of the fluid streams going in and going out. So you have a velocity on both streams. So similarly, you'll have 1/2 m1 v1 squared and 1/2 m2 v2 squared. That represents the kinetic energy. of the entering stream and the kinetic energy of the leaving stream. And yes, that's a separate energy form, separate from internal energy. If you could think about it, some massless particle, or excuse me, not massless particle, but some particle can have its own internal energy, like how much energy it contains in and of itself. Like if I took a baseball and I threw a baseball, it's going to have its own internal energy, whether it's at rest or in motion, right? But if it's in motion, it also has an additional kinetic energy. And in addition, what we learned in projectile physics is that the distance it is from, let's say, the center of mass of this vessel is going to represent the at least the delta of the potential energy of the system. So let's go ahead and look at that. And those are the potential energies of the fluids entering and leaving the system. But there's an additional work caught up in each of these streams, and we're going to call that flow work. And we're going to talk about that more in the next video. But suffice it to say, this is the energy balance of our system, right? So, other places like to put it like this, so I'll go ahead and do that. That the change in energy equals the energy in minus the energy out. And then plus energy generated. And in this course, we're not even going to look at the energy generated, not really that much. So, but in general terms, our energy in is going to look like, our Q, our WS here, shaft work and Q, and then it's going to look like also our mass term times our U1 plus 1/2 V1 squared plus GH1. And then similarly, our energy out is going to be equal to M2 times our U2 V2 squared GH2. And then we have some flow work in minus flow work out. And we've not defined what that is yet, but that's what you're going to find. So I forgot to even define what the change in energy looks like. But that's what we're going to talk about in the next video is the flow work. But this is the bare bones of the energy balance, right? So again, in chemical engineering, you're not necessarily so concerned with kinetic and potential energy changes, but we're trying to be all-encompassing here in our definitions so that we can have a strict, clean, crisp definition for understanding in its entirety of what does the energy balance in our system look like. How is it derived? How is it defined? All right, so again, right now where we're at is we've got two ways energy transfers through non-matter phases, let's say, or ways, right? So we've got a physical way and then a heat transfer way. And then we have three different forms of energy coming into the system or out of the system, as well as a fourth form of energy, but it's not energy. It's called work, flow work. So we're going to define that here in a moment. All right. So I'll see y'all next video for the rest of the explanation.